Okay, I think we can start. It's 35 past 8, so I would start, Guido. So welcome everyone. Good morning, good afternoon, good evening, or maybe even good night, according to the location where you are now. Just a brief introduction of what we will have today in the first half of this second day of the DRCN 2021. We will start with the second keynote of the conference, which will be given by Dr. Masakatsu Fujiwara. Then we will have a session, a technical session, session 4 on 5G with 4 contributed presentations. Then after the coffee break, we will have an industrial panel, which is on open solutions for the next generation telecom infrastructure. So now I leave the floor. I ask Dr. Masakatsu Fujiwara to start the sharing of the screen and check the audio. And while I do a brief introduction of him, I ask him to do this test. Okay, so I hope you will enjoy the program of today and the rest of the conference. So please, let's hear to Dr. Fujiwara.
Thank you, Chairman. Can you hear me?
Yes, we hear you. So Dr. Masakatsu Fujiwara is the Vice President and Head of Communication, Traffic and Service Quality Project at NTT Network Technology Labs in Japan. And his main research interest, his work is focused on innovative network management and operation by AI and data analysis. So he's going to give us a keynote, which is titled Entities Challenge Towards Self-Evolving Zero-Touch Network Operation with AI. So please, Dr. Fujiwara, the floor is yours. When you are ready to share, please do it.
Okay.
If you want, I can tell you 5 minutes before the dedicated time ends. Consider you may have between 35 and 40 minutes. So we leave some minutes for Q&A at the end of the presentation.
Okay. 45 minutes is too long for me, so I think...
No, 35 to 40.
35, okay.
To 40, okay.
Okay, I'll make it brief.
Okay.
So, okay. Thank you, Francesco. And good morning to people in Italy, Europe, and good afternoon, people in Japan, and hello to all over the world. Sorry. My name is Masakatsu Fujiwara, and from NTT. And thank you for giving me this opportunity for my keynote speech. And I was really looking forward to visiting Milano, Italy this time. But unfortunately, I'm still in Tokyo and sitting in my home, in my desk. So, but anyway, I'm very happy to meet you online now. And today, I'll talk about entities, R&D activities about network operation. My presentation title is this here, Entities Challenge Toward Self-Evolving Zero-Touch Network Operation with AI. These are today's topics. First, I'll talk about zero-touch network operation. It's a short-term or mid-term goal. And secondly, I'll talk about our future network vision called ION. It's a long-term vision, like 2030. And finally, I'll explain our future vision beyond zero-touch network operation and how we go forward more than current operation scheme. Okay, let's start from number 1 to a zero-touch network operation. So before introducing about AI or zero-touch operation, I would like to show you some important changes that affect NTT. NTT is the biggest network operator in Japan. And the first issue is aging population. Lack of workforce is becoming critical and for many industries in Japan. And this is also true to us, NTT. I'll talk about it more at the next slide. The second issue, second issue is digital transformation. We need to transform how to do our business drastically by using digital technology. We still have a lot of old business process like this picture, and network maintenance and work procedure. We really need business process re-engineering, BPR, in order to find more efficient way, more efficient procedure by using available technologies today, like AI or data analysis. Okay, this is the aging issue at Japan and also in our company, NTT. The left chart shows Japan's population, working age population. The peak was here around 2010. Since then, the number of possible workers gradually decreasing. 10 years ago, it was a peak, but this trend, decreasing trend, continues in the future. And right figure shows the demographic change of our company, NTT. As you can see in this figure, many of our employees are over 50, between 15 to 60. And typical retirement age is 65 years old in NTT. So that means in coming 5 or 10 years from now, 30% or 40% of our employees will be retiring. And we become very short of skilled engineers in 5 years. So we need to replace the skilled engineers' work with the system or machine work. For this purpose, I believe AI and data analysis will become key technology in this area. Okay, I'm showing by this slide that operators' business process, design the network facility and deploy the equipment, and finally operate them. Design, deploy, operation cycle. And in the past, network was king for operators. I mean that the most important asset for us was the network. It's most precious and most expensive asset for telecom company. And the efficiency of the investment to the network was the key factor. And so in this in our old process, the top priority was to make the most of the network asset, network resources. And in this figure, the circle size design, deploy operation, the circle size indicate the total cost of each process. And in the past, the designing process was important. It's a process to make a plan, to make the most of, to utilize our network assets. And the human cost was relatively low in the past. So the human was working for network, not network work for human. This is in the past. And we see the change. This is the future business process we see. I mean that OPEX, operational costs, will be bigger and bigger. Human resource will be the precious resource. And network equipment will be cheaper and cheaper. I mean, thanks to the technology like cloud, virtualization, open source software, white box switch, such technology will make our network equipment less expensive. So now we need to this operation cycle. We need to focus on this part. We want this cycle smaller and smaller. That means OPEX to reduce OPEX. So how to make our operation process simple and efficient is a key factor for operators. The next slide. This is the autonomous zero-touch operation autonomous loop. And yeah, many of you have already seen this loop, this chart. And we have a lot of systems for monitoring and controlling, but human make a judgment today, and human make a decision what to do next. And each systems, we have a lot of systems, but these are silo and those are not connected, independent. One human operator use a lot of systems, and today they are not connected. The idea is to connect all this loop fully automated based on data. The center of this chart, this is data, and inside the data includes both inside the network and also outside the network. So each work process and each human judgment should be automated and should be replaced by system. And also each work process should be connected. And we need to utilize data and AI for this vision. And from now, I would like to show you some of the use case or examples of our activity. And okay, let's start from MMS. I use the video content to explain this activity, but this is for innovation for inspection of the cables, poles, and okay, let's see the video. It's okay. Can you hear me? Sorry, this
NTT グループは1200万本の電柱、211万 km にも及ぶ通信ケーブルをはじめ、膨大な通信設備を所有し、その保守点検業務には膨大な労力と時間を費やしています。そこで NTT アクセスサービスシステム研究所では、安心安全な社会インフラサービスを提供するため、設備運用の改革に取り組んでいます。ここで我々が目をつけたのが、モービルマッピングシステム、通称 MMS と呼ばれる計測車です。MMS は近年測量地図業界などでも活用されており、GPS、カメラ、レーザースキャナーなどを搭載し、道路周辺の設備を計測することで、高精度な 3D この点群データに対し NTT 独自技術を用いることで、電柱、視線、ケーブルといった設備のみを 3D モデルとして自動検出することができます。では、この技術によって点検業務がどう変わるのか見ていきましょう。現在の点検では、点検者が電柱を一つ一つ歩いて回り、電柱のたわみなどの状態を目視で確認するため、点検者によって点検結果に差異が生じます。ケーブルの地上高も同様に目視で確認し、地上高不足と思われる場合には測定管を使って計測します。
Dr. Fujiwara, sorry, can you please stop one moment?
これに対し、
I'm sorry, sorry to interrupt. We hear very loud the Japanese speech, but I think you were speaking behind. So yeah. We couldn't hear you translating, I think you were translating, but we basically heard just the Japanese speak. So I'm sorry to interrupt you, but perhaps you can share the video. If you don't need sound from the video, you can just show the video without the sound, and you can talk on top of it.
Okay.
I'm sorry about that.
Okay, no problem. But I think that if you watch the video and then you could understand that the main part already finished.
Okay.
I wanted to say that using that data and combined with our AI technology, object modeling technology, we can extract poles and the cables, and then such kind of inspection was done automatically in many parts of our country. So we started to use such technology for inspection. So that's I wanted to say.
Okay.
Okay, let's move to the next slide.
I think you should go back to sharing of the slide. Okay, now we see them. Please.
Okay. The next thing, the anomaly detection technology using AI. We have already developed the for detection software, anomaly detection software, using deep learning or autoencoder method. And the data input is MIB data or syslog data from the servers or routers. And the normal state is run by using such data. And then at the surveillance phase, this autoencoder can calculate and some anomaly degree, and then sort of the risk score using autoencoder. Then when the degree of the anomaly exceeds the thresholds, and the alarm comes to the human operator, then the state is detected as anomaly using this data. And we have already implemented this system to the commercial system and in the actual field. And in some case, we could catch some of the bad signals beforehand, several hours before the actual failure came out. Okay. So let's move to the second topic, ION. So this is our long-term concept, innovative optical and wireless network. So what is ION? It's a combination of broad range of technologies for all photonics network, and the intelligent part, what we call cognitive foundation, and for it also includes the computing, digital twin computing part. So I'll again use some video to introduce some of this concept. Please wait.
Innovative optical and wireless network.
Oh, wait. Yeah. Okay, is this okay?
Innovative optical and wireless network, ION, is a future communication infrastructure with photonics technology at its core that is being attempted by many companies, including NTT. ION is made up of 3 elements: all photonics network, digital twin computing, and cognitive foundation. An all photonics network applies photonics technologies to information processing, in addition to conventional optical fiber communications. By further advancing nanophotonics technology, in the future, we aim to achieve power consumption levels of 1/100th the current level, even for circuits inside the devices. An ultra-high capacity and ultra-low latency network can be created by allocating optical waves for each path and using an optical transmission path with space division multiplexing, wavelength division multiplexing, and other multiplexing, in place of conventional IP packet-based routing for transmission through optical fibers as well. ION will not only expand communication between people, but also impact various other fields, such as enabling artificial photosynthesis. The digital twin computing that we propose is a computing paradigm which expands on the concept by enabling humans and things in the real world to be recreated and interact without restrictions in cyberspace, with digital twin operations, computations to exchange, fuse, replicate, and synthesize multiple digital twins. While conventional digital twins have been mainly used for digital observation or control of physical objects. Digital twin computing aims to expand the scope of such digitalization from things to humans and enhance communications among humans and things in cyberspace. By enabling interaction between diverse digital twins in cyber and physical space, digital twin will instantly estimate the image for the next moment and reflect it in the real world to smoothen various activities in society, starting with urban mobility. It can also support superior decision-making by predicting the future of people and the world. To instantaneously process such large volumes of information, we require computing power greater than that of existing computers. In the future, networks and computers powered by photonics technologies will make digital twin computing possible, and people will be able to digitize themselves along with society as a whole, letting them interact with each other in virtual space. Cognitive foundation refers to a framework that enables one-stop configuration, setup, management, as well as operation of all kinds of IT resources, including IoT and even user devices, in addition to clouds and networks. An intelligent cognitive foundation with diverse AI and other technologies will determine the condition of the information platform in real time and optimize it as a whole. It can help develop a user-friendly operation that is fully automated and autonomous without making users needlessly concerned about the existence of a network and the differences between technologies and devices. ION aims to create new value through a future communication.
Okay, and this is a concept of the ION, but it is not just concept. It is not just a theory. And now we're doing some proof of concept project. I have one more video, and I like this video, so please watch one more. This is for autonomous driving of agricultural vehicle.
Looking to the future of agriculture in Japan, smart agriculture is being rapidly developed, and its commercial application is being researched. In collaboration with Hokkaido University, Iwamizawa City, SmartLink Hokkaido, Kubota, and Hitachi Solutions, the NTT Group is conducting a world-leading demonstration experiment to achieve Level 3 driverless autonomous driving of farm machines. To achieve autonomous driving through remote monitoring and control via a telecommunications network, this experiment employs NTT Laboratories' leading-edge network and information processing technologies, which constitute NTT's new network concept, ION. In Hokkaido, it is common for farm machines to run on roads to move from one farm field to another. It is not practical for a single network to cover the extensive area in which farm machines are employed. To achieve autonomous driving over a wide area through remote monitoring and control, it is necessary to selectively use several networks, such as a carrier 5G network and local 5G networks. However, simply switching networks after quality degradation cannot prevent the communication of video and control from being disturbed. It also changes the network addresses and thus requires farm machines to re-establish their connections. Radio quality prediction technology is a solution to this issue. It uses machine learning to estimate and predict the communication quality of multiple wireless communication networks, such as a carrier 5G network and local 5G networks. This technology can determine when a farming machine crosses the boundary of network coverage areas, predict local degradation in communication quality, and decides to switch networks before quality degradation occurs. Upon receiving this decision, E2E overlay network technology uses SRv6 to switch networks while maintaining the same IP address and communication method, thereby making re-establishment of connections for video and control communication unnecessary. These two technologies work together to enable safe and smooth self-driving.
Okay, and so never stop to achieve never stop wireless communication. We use a prediction, network quality prediction technology, and using AI. And this is a good example of ION supports the future use case, I think. And let's go back to the slide. I have only 5 minutes. Okay, let's go to the last part, beyond zero-touch network operation part. And this is my slide title again. And you might find that the title includes the self-evolving zero-touch network operation. And I mean by this self-evolving, it's a operation system or algorithm enhance itself or strengthen itself, getting better according to the change. We need to catch up the change. That's what I wanted to tell you by self-evolving. And to catch up the change or overcome the change is the next our target. Like disaster and pandemic and even smaller change, software update. The change happens every day, every year. Big change. Yeah, this is a picture of our Japanese earthquake or the aftermath of the tsunami just 10 years ago. And that it is not once in 100 years. Earthquake or typhoons comes to Japan every year. Yeah, this year big typhoon hit Japan and heavy rain. You can see the picture and also the earthquake. Our building got destroyed and also cables facilities damaged terribly. And such catastrophic event, in addition to such catastrophic event, change happened every day in the network. And it is not easy to cope with these daily changes. AI or machine learning isn't necessarily robust against change today. So it needs the parameter change, relearning. So how can we prepare for unexpected problems is our focus. And I have only a small short time, so I just wanted to tell you this use case. And if we want to go beyond the human judgment, and AI need to go beyond the data. So one of the biggest problems to cope with the unexpected event or catastrophic event, and the problem, we have no running data, so no examples to run. And without data, running data, AI itself cannot do anything. So our idea is artificially create the running data in the cyberspace. And we try to build the digital twin of our network. And it's like a simulation, perfect copy of the real network in the data center. And we make a failure and some events and get the data. And we can, if we can generate virtually the events such as disaster, and we can monitor and we can get the data, and then AI will handle such kind of data. And this is one approach for self-evolving operations. Okay, and that's all for my presentation. And yeah, grazie. Thank you very much.
Thank you very much for your presentation, Dr. Fujiwara. Is there any question from the audience? Please raise your hand and I will give you the possibility to ask. Or even you can write in the chat and I read the question for you. So while we wait for the attendees to, okay, there is maybe a raised hand. Dominic Schupke, please. Dominic.
Yeah, thank you very much for this visionary presentation. You were talking about the predictive maintenance case where you could predict failures. Can you detail what failures were successfully predicted and maybe what couldn't be predicted?
Okay. Thank you for your question. I talked about the Diano's case, autoencoder anomaly surveillance. And what we did well was for the servers. And what we are now trying to approach is router case. I'm not sure how, but servers, we can get a lot of the data, and this system can detect. We try routers, servers, and also hardware systems, and the servers worked very well. And routers, we have not yet succeeded yet.
Okay, thank you.
Any other question from the audience? So meanwhile, I just make a question or observation, basically. What do you? So we are in these years. AI-driven applications are very relevant and very. I mean, they are attracting a lot the attention of researchers and practitioners and so on. But do you think there is a limit in the penetration of AI in your business, in your networks in general, in the services that they can support?
Mm-hmm. Thank you for your question. I think that we will start to use AI technology for such purpose, but we One problem is AI's decision. AI's judgment is a black box. AI can tell us something wrong, or we should do that, but we cannot get why we need to do that. AI only gives us the answer and suggestion, but we need to explain to our customers why we do this, why you need this action, this operation. Today's AI technology cannot explain why AI choose this way. So if we can achieve such AI judgment explanation, I think that AI will penetrate more and more to our business. Can I answer your question?
Yeah, sure, for sure. So I agree that in general there should be an on-top control, which at the moment is still delegated to experts of the field that need to, say, double check and validate the decisions of AI. Mm-hmm. And about anomaly detection, since we are discussing about that, do you deem there can be types of anomalies that even humans do not have ever experienced in the network that AI is able to identify? And in case yes, did you have any experience in your use cases about that?
Yes and no, and it depends. And for actually, in a real case, we could find, and we use just as a warning, and operator can notice by this system, and so. And our operator side say that please, how can I explain this? And I wanted to say that yeah, that's the case, and so we use this this system. The operator side requires only give us the alarm when 100% it's a failure, and we tune such a way, and if we find something wrong, but when system doesn't think it's 100% failure, the system might be silent, and we use such a way, because currently it's only one of the many systems to detect the failure. So when this system says it's anomaly and it's a 100% failure case.
Okay. Guido, do you have any question, please?
I have a non-technical question, more curiosity. You mentioned in your very nice presentation several cooperations of NTT with universities and research centers. Mm-hmm. So I was wondering if these cooperations are mainly entirely supported by NTT, or the Japanese government, in a sense, provides fundings for these cooperations?
Oh, the agriculture vehicle case, asking.
I mean, generally speaking, but if you want to refer to
that. In some case, we fund to the universities, but because many Japanese universities are not so rich, so we fund. And but when we cooperate with companies, foreign companies like Orange or Nokia, Ericsson, we are equally, and each company fund, and not one side pay the money. Both sides pay the research funding. That's the case, normal case.
Thank you.
Thank you very much.
Okay, thanks again, Dr. Fujiwara, for his very interesting talk. I think there is another hand from Dominic, another question from Dominic. I see a raised hand.
Yeah, if I may only.
Please, please.
Yeah, so one question would be, how do you see satellite communication and high altitude platforms in this game for these disastrous cases like earthquakes? How do you integrate it, especially in this kind of fully automated way that you were presenting?
Thank you for your question. Asking, we use satellite to satellite communication to complement the damaged cable.
Yes. Yeah.
Yeah.
How is that integrated in the overall optimized automatic system?
Yes. We use satellite and also the broad range of the communication system to recover from such a big disaster, because our cables, pipes, all damaged after the disaster and tsunami, and it takes few months to recover, and also the building also washed away, and so a wireless communication should be the faster to recover. So we utilize satellite and also the wireless communication to recover from the disaster. Only even for the fixed communication. Thank you very much.
Okay, there is a question from Kohei Shimoto, please.
Yes, thank you, Fujiwara-san. It's a nice talk. And I have a question. You present the application of AI to network management tasks. And you are applying the established machine learning technique, or the state-of-art machine learning technique. But do you think that you need to innovate the machine learning algorithm itself for the network management purpose? So if you have any specific area you want to pursue in the machine learning technique, I'd like to hear.
Okay, thank you for your question. Yes, and the researchers about AI doing research all over the world, and we are network operators, and we utilize the domain knowledge about network operation, and also import the knowledge from AI researchers. And we are now, we just, what we are doing, what we are adding to the machine learning or AI is not the engine itself, but the, how can I say, the how to make AI convenient to use, like parameter tuning or relearning, when we should relearning, and what kind of parameter tuning we need when. And because only researchers, if the researchers can make a tuning and relearning again and again. But in our case, no AI expert use such kind of system. So we try to add some additional AI technology to make things easy. Because this is we are part of operator. Can I answer your question?
Oh, yes, I think so. And of course, NTT is a big company, and you have many researchers in the AI area. So that maybe I think you collaborate with AI researcher in your labs, and
yes,
so,
yes.
Yeah.
And the object modeling technology like poles and cables and such technologies are imported from our colleagues, not our internal laboratories. And we have a variety of AI researchers, and we collaborate and utilize for network operation purpose.
Okay, thank you.
Thank you very much.
Okay, thank you, Dr. Fujiwara. If there is any other question, I invite attendees to contact offline Dr. Fujiwara, so we can go. It was very interesting talk, and thank you again for joining us with your talk.
Thank you.
So,
grazie.
Thank you.
Thank you very much.
So now we are going to have 4 contributed presentations for papers. So we will have the session 4 on 5G, and I've seen that all the 4 speakers are now logged in. So I will show the video from my laptop, and then I will leave the floor for Q&A to each of the authors one after the other. So let me share the first video. So the first video is here. Okay, so the first presentation is from Hiroki Ikeuchi, and Hiroki is from NTT Corporation in Japan. So I will just start the video. I ask Hiroki to, if it's the case, to turn on the video, maybe even later when there is the Q&A session. And now the video is on.
I want to talk about a new method for designing the UAV trajectory for network surveillance after a disaster. Here is the outline of my talk. First, I will start with the introduction and then explain the problem we consider. When a natural disaster, such as earthquake, heavy rain, or storm occurs, correct assessment of the damage situation is very important for the rapid restoration of the network infrastructure. For example, as shown in the left figure, after a disaster occurs, emergency vehicles need to be dispatched to restore the infrastructure. However, if the road network is partially cut off, it is necessary to know which route of the vehicles take. Or if you want to repair the aerial cable network, it is necessary to know which part of the network is cut off in the first place. In recent years, UAVs has been attracting attention as a means of assessing such damage. UAV cameras can obtain more detailed data than survey aircraft or satellite cameras. Recently, disaster drones equipped with GPS and capable of long-range flight have also been introduced. Taking such background into account, we now consider the following problem. If you want to understand the damage situation of a target network, such as road network or aerial cable network, how can you determine the flight route of the UAV to efficiently collect such information? Generally, it is difficult to survey the entire area of the network in detail. So in reality, it is necessary to prioritize links with high importance and high probability of damage, such as links located in hazard areas. Besides, it is necessary to consider the limitation of the UAV battery and the time limit of survey. In this presentation, we formulate the problem of network monitoring by UAVs as an optimization problem and propose a method to solve it. The goal is to calculate the optimal UAV trajectory based on these priorities and constraints, considering network surveillance as a graph covering problem. Now let's move on to the formulation of the problem. We consider the target network as a graph in a two-dimensional plane. We collect information by taking pictures of the edges of the graph. In general, disaster vulnerability is often published as a hazard map. We assume that the target area is divided into the hazard area and non-hazard area, and the edge failure rate per unit length in each area is given as a lambda h and lambda n, respectively. Of course, lambda h is larger than lambda n. Besides, each edge is assigned an importance according to the importance function f. This can be defined based on the topology of the graph or domain knowledge, such as whether the road is designated as an emergency transportation road. Next, we define the area Sk to be covered by the UAV camera. We assume that the UAV camera can capture a disk area of radius r in a single shot. For convenience, we assume that the points that can be photographed are discretized and indexed by k. Based on this model, we then define the utility function for the optimization problem. The utility is the expected value of the weighted number of the found failures. The definition is written like this. First, this part is the probability that the edge Ej is cut off. It is calculated from the length of the part belonging to the hazard area and non-hazard area. The importance weight, denoted by f of Ej, is attached to it. We need to pay attention to this summation. This summation only consists of edges that are completely covered by the UAV camera. In other words, edges that are only partially covered by the UAV camera do not contribute to the utility. For example, this edge does not contribute to the utility. This definition is based on the idea that if the unphotographed part of an edge is disconnected, the edge will not function in the network, and therefore the information can only be meaningful if the entire edge is observed. According to such a utility function, the optimization problem is formulated like this. The objective to be maximized is the value of the utility defined according to the location to be photographed. In the example in the right figure, the value of the utility is calculated from the green disks. The constraint is the path length of the UAV. In this example, it is the total length of the orange line. If the set of the green disk is the same, but the order of visits is different, the path length will be different. So we need to calculate not only the set of indices k, but only the order of them, denoted by the capital K. Also, we assume that there is a UAV base, which is the starting point and goal point. This is the formulation of the optimization problem. This problem has the following difficulties. First, the utility function for shooting point k is not additive due to this summation. In addition, calculating the cost d of k is a traveling salesman problem, which is NP hard. To overcome these difficulties, we first convert this problem into an edge selection problem. We earlier formulated a problem of deciding shooting, but now we want to convert it into a problem of deciding which edge to cover completely. By doing so, the utility function becomes additive with respect to the choice of edges, and the greedy method can be applied as described later. The calculation of the cost d of k is performed with an approximate method. After determining the shooting spots that can completely cover the selected edges, d of k is obtained by approximately solving the traveling salesman problem. The details of the algorithm are described here. The outline of the algorithm is almost the same as the general grading method. The algorithm tries calculating the utility U and cost D for all candidate edges. One edge is decided to be adopted according to the grading method. However, if the cost of adopting the edge exceeds the constraint, we stop adopting the edge and remove it from the candidate list. This procedure is repeated until the candidate list becomes empty. For the greedy edge selection part, we have considered two methods. In algorithm 1, we simply adopt the edge with the largest increment of the utility. In algorithm 2, we calculate the ratio of the increment of the utility to the increment of the cost, and adopt the edge with the largest ratio. By doing so, we can expect to select edges with less excessive cost expenditure. As I said earlier, approximate calculations are required to determine the shooting points and the order of visits to the selected edges. For example, as shown in the figure on the right, if we decide to cover edges E1 and E2, we need to determine the minimum set of the candidate shooting points that completely cover them. In this case, we can see that S1 and S3 can cover them. This can be solved approximately by a process similar to the minimum point coverage problem. Next, to determine the route connecting the obtained sets of shooting points, the traveling salesman problem is solved by approximate methods such as the grading method. Now I explain the numerical variation of the proposed method. For the numerical variation, we use the simple graph to evaluate the performance and road network data to verify the method in a realistic case. We first start with a basic example. In this evaluation, we compare the two algorithms with the exact optimal solution using this grid graph that we have seen several times. There are 12 edges in total. The red edges have high importance. Aqua area indicates a hazard area, and edges located in this area have a high failure rate. We assume that the UAV starts from the origin 0, 0 and comes back. Here are the results. First, please look at the left figure. The horizontal axis is the flight distance limit, and the vertical axis is the utility. The results of the proposed algorithm 1 and 2 and the exact optimal solution are plotted. We can see that the green dashed line, algorithm 2, almost agrees with the red dotted line, the exact solution. On the other hand, the blue line, algorithm 1, sometimes outperforms algorithm 2, but its utility fluctuates greatly. This is because algorithm 1 greedily chooses the edges with the highest utility, which sometimes leads to the behavior that consumes the budget greatly. Figures B and C show the results when we change the parameter of the failure rate and the importance. We can see that the proposed algorithms are good approximations of the exact optimal solution in almost all regions. Next, I will show you an experiment using road network data. In this evaluation, we use the road network of Shibuya City in Japan, an area prone to landslides. The graph is based on OpenStreetMap data. The number of edges is 374, which is too large to obtain exact optimal solutions, so we need to apply the proposed algorithms. The red roads are designated as emergency transportation roads by the government, and they have high importance. Black roads are other general roads. The brown area is designated as a landslide hazard area. We use a 200-meter square grid as the UAV shooting point, and the radius of the photo coverage is 200 meters. We assume the UAV base to be located in the city hall. Here are the results. The upper figure shows the results of algorithm 1, and the lower figure shows the results of algorithm 2. This table summarizes the utilities we change the flight limits and the policy. The policy is determined by the pair of the parameters of the failure rate and the edge importance. We can see that algorithm 2 outperforms algorithm 1 in almost all cases. The figures show that algorithm 2 conserves the flight budget because it takes into account the ratio between the utility gained and the cost consumed. On the other hand, algorithm 1 spent much of the flight budget by flying between distant edges. Next, I will show you the obtained trajectories with different budgets and discuss the characteristics of each algorithm. We can see that algorithm 1 picks up a lot of edges of high importance that are located in mountainous areas. Algorithm 2, on the other hand, picks up many edges in the urban area while moving along the road. This is because algorithm 2 tends to select edges that are closer to the already selected edges, since they require less additional cost. So, to sum up, we can conclude that algorithm 1 should be used when the edges to be surveyed are widely scattered in the target area, and algorithm 2 should be used when we want to move along the road and survey the area exhaustively. Here is the conclusion of my talk. We have formulated the UAV trajectory optimization problem and proposed two types of greedy algorithms. In future work, we are planning to consider more realistic factors, such as the flexibility of UAV cameras, geographic conditions, and network connectivity. And we are also planning to extend the algorithm to multiple UAV cases. This is the end of my presentation. Thank you very much for your attention.
Okay, so thanks for the presentation. Now I'm going to make Hiroki Ikeuchi presenter so he can answer questions. Any questions from the audience, please raise your hand or write the question in the chat. So meanwhile, I have a question, and it's about scalability. Of course, you have dealt with greedy. You have developed two greedy algorithms to deal with scalability, but also these two algorithms, are they facing scalability issues? So what are the times required to solve your problems in the use cases that you have considered?
Thank you for your comment. You're asking our scalability greedy method. Scalability depends on the complexity of the topology, but empirically, the calculation time depends on the size, and I think that if the number of the edges is about around 100, the calculation will finish within 1 hour, about 1 hour. So, and maybe our algorithm is maybe the order of the 3 or 4 fourth power of number of edges. So it is practical when the network size is has maybe several hundreds.
Okay, thanks. So there is time for another question. Dominic, please.
Yes, thank you very much for your talk. One question I have, how do you deal with cases where the camera vision is obstructed, for example, in a tunnel or so?
Sorry, I can't hear you.
So I understood that currently you assume that you always have a perfect camera vision, right?
Yes.
And how do you deal with the case when something is happening in a tunnel or so, when the camera vision is obstructed, so it's not perfectly seeing the environment.
Yes, that's a very important question. So yes, in the present work, I assume that the photo coverage is perfect, but in the real case, some obstacles or the camera problem can occur. So the maybe it will be a future work, but we need to consider the height of the UAV and the more detailed characteristics of the cameras. But they are maybe the future work. Thank you.
Yeah. Okay. Good. Thank you. Thank you for your answer.
Okay. So let me thank again Hiroki Keuchi from NTT for the presentation and for the exhaustive answers. So now we can move to the next speaker, to the next video. The next video is the next paper is from Jingjie Shin, and it's titled DNN-based multi-false localization for 5G coexisting radio and optical wireless network. I'm going to share the video now.
My name is Jingjie Xin from the School of Electronic Engineering, Beijing University of Posts and Telecommunications of China. It's my pleasure today to make a brief introduction to our work. The topic is DNN-based multi-false localization for the 5th generation coexisting radio and optical wireless networks. The presentation is organized into 5 parts. Let's begin with the background. As we all know, the 5th generation mobile network is characterized by diversified services with more disparate and stringent technical indicators compared to the 4th generation. The 5th generation should be enhanced in terms of data rate, transport latency, traffic density, and energy efficiency. To deal with such challenges, designing a high-rate, reliable, and resource-efficient framework for the 5th generation is necessary. Optical networks have good performance for future high-speed and large-capacity service transmission. Therefore, the 5th generation coexisting radio and optical wireless network that takes optical network as backhaul becomes an emerging research direction to cover with requirements of the 5th generation mobile network. Then, we simply introduce coexisting radio and optical wireless deployments, as shown in the left figure. Optical wireless spectrum is used to increase existing radio frequency responses. Optical wireless communication application comprises of different networks, including visible light communication, free space optical communication, light fidelity, and optical camera communication. A typical solution for coexisting radio and optical wireless deployments is presented in the right figure. Wi-Fi-enabled luminaires can provide data access to stationary and quasi-stationary mobile users in the front-haul network, which can alleviate congestion and free radio frequency resources. Next, we'd like to interpret why we choose DN to solve multi-false localization problem. When there are faults in the network, it may cause quality of service degradation or even cause service interruption. Network operators need to accurately locate the sources of faults and then fix them as soon as possible. However, theoretical analysis shows that the multi-false localization problem belongs to the NPC problem in optical networks. More important, the complexity of multi-false localization algorithms increases linearly with the expansion of network scale. Since the structure of the coexisting radio and optical wireless network becomes more complex. The amount of data to be processed for multi-fault localization increased greatly. Lately, deep neural network has been widely concerned and researched. It has a natural advantage in processing massive data. Therefore, we apply DN to multi-fault localization for coexisting radio and optical wireless networks. Then, we will introduce the multi-fault localization problem and the solutions of our work. As shown in the left figure, with the optical wireless access node A, the link CD, and the link KF have failures, all destination nodes of interrupted light passes can report alarms. However, different combinations or faults can result in the same set of alarms. For example, the failure of the link CE can also cause destination node D and destination node K to report the alarm A3 and the alarm A1 respectively. The failure of the link DK can also cause destination node F and destination node K to report the alarm A4 and the alarm A2 respectively. The destination node can determine which node or link the light path has failed according to received alarms. The traditional multi-fault localization method is based on a bipartite graph between suspected faults and received alarms. The objective is to find out the most likely fault set with the least number of faults based on received alarms. Next, we'd like to introduce our DN-based multi-fault localization methods. At first, we'd like to introduce our multi-fault localization framework, as shown in the left figure. Network topology is divided into multiple domains, each managed by a separate network controller. In our work, we only focus on fault localization within a subnet. In the control plane, the network controller is used to manage the distribution of monitors installed on transmission nodes. When faults occur, the values of some parameters may exceed the threshold. The destination nodes of interrupted services can report alarms. Then, the controller automatically collects alarm data. The DN is integrated in the controller to locate faults according to received alarm data. Then, we'd like to simply introduce the principles of two neural networks adopted in our work. In BP neural network, each layer is fully connected. It is a multi-layer feed-forward neural network, which is trained according to the area back propagation algorithm. The LSTM neural network has good performance in long sequence training and can save input for a long time. Meanwhile, it can effectively reduce the risk of gradient disappearance through changing the weight of the self loop. Next, we begin to introduce our DN-based multi-fault localization methods. Our work mainly focuses on failures of access nodes in the front haul network and failures of fiber links in the back haul network. Since optical wireless nodes and radio nodes only exist near the edge of the service side, these nodes only provide functions of uplink and downlink. They don't take responsibility for information transmission. Therefore, in our work, the failure of radio nodes or optical wireless nodes is equivalent to the failure of the link between them and the nodes connecting them to the backhaul network. The specific DN-based multi-fault localization model is shown in the right figure. The node set of this model is sequenced to form an alarm sequence from N0 to N13. The state of a node is represented by 1 once this node alerts, otherwise it's represented by 0. The link set of this model is sequenced to form a fault sequence from link 1 to link 20. If a link fails, the value of the corresponding position in the fault sequence is changed from 0 to 1. The input and output of two DNNs are alarm sequence and fault sequence respectively. Our goal is to output locations of the faults according to alarms reported when multi-faults occur. Next, we'll show some results of our simulation. training dataset we used are generating from the simulated network as shown in the left figure. Some specific simulated parameters are presented. Table 1 summarizes some key parameters of our two trained DNNs. These three figures present the mean squared error of two DNNs when the number of faults is 1, 2, 3. We can find that when the number of iterations is 140, 150, 250 respectively, two DNNs converge. Moreover, the LSTM neural network converges faster than the BP neural network. These two figures respectively present the localization accuracy and localization time of two DNNs. When the number of faults is 3, the localization accuracy of two DNNs both exceeds 87%, and the location time of two DNNs doesn't exceed 4 seconds. Moreover, we can find that the performance of the LSTM neural network in both aspects is better than that of the BP neural network. Here comes the conclusions of our work. We introduced the DNN-based multi-fault localization methods for the 5th generation coexisting radio and optical wireless networks. Two methods both achieve fast multi-fault localization and high localization accuracy. The performance of the LSTM neural network is better than that of the BP neural network. In the future, we would like to consider training a neural network which could realize the localization whatever the number of faults is. That's all. Thanks for your attention.
Okay. So time for questions. There is, I think, the speaker is already on. So if you want to activate your camera, you are very welcome to do so. So while we wait for questions. Hello. Hello. So I see one raised hand because it's yours. So I am going to lower down your hand. Okay. So any question from the audience? I have one on the inputs. You have said in your presentation that you have a pattern of inputs which represent the alarms for each node. So if you have 14 nodes, I guess you had 14 nodes in your use case, you had a vector of 14 binary values. Do you think, so first question is the alarm just a faulty or non-faulty light pattern, faulty or non-faulty alarm? So is it only binary, or there are possibilities to consider multiple alarms in your use case?
Can you hear me?
Yes, we hear you.
Okay. In the 5th generation large-scale network scenario, the number of network devices and the links has increased dramatically, and it is difficult to obtain the exact number and location of faults. Deep learning has natural advantage in processing massive data, and it can make decisions according to its perceived environmental states. If we deploy our models into actual network, it should be retrained. It should be retrained by actual data, and the actual data should be pre-processed. I think so.
Mm-hmm. Yeah, of course. Did you optimize somehow the parameters of the hyperparameters of your neural networks? I mean, how you decided the structure? How did you decide the structure of the LSTM that you used or the BP network that you used?
I think this question can be viewed as a multi-classification, multi-label problem, and each input sample can have multi-labels. Just like if there are a dog and a cat in a picture, this picture should have two labels, respectively the dog and the cat. Therefore, in order to promise the generalization ability of our model, we can only adjust the models based on training data. We can split data into three parts: training data, validation data, and test data. During training, we monitor training loss and validation loss, as well as important indicators such as localization accuracy, mean square error, and others. Once we find the performance in validation data began to descend, this means the model is overfitting. Then we can also use regularization methods and continuously train models to modify parameters until models achieve the best performance. That's all.
Okay, thank you.
Thank you.
Other question? Any other question from the audience? Okay, so if not, we can move to the next presenter, to the next presentation. So the next presentation is from Kexin Wu from BUPT.
Francesco, excuse me. I want just to mention that Kenshi Wu sent us an updated version of the video. I don't know if you have...
I have downloaded it yesterday. I'm not sure it's the latest one, is it?
I have just copied it in the Dropbox folder.
Yeah, but I have received via email. So now let me. Okay. It should be the latest one. So I am going to promote Kexin to relate to presenter. Okay. And share the video.
Good morning, everyone. My name is Wu Kexin. I come from Beijing University of Posts and Telecommunications. It's my great honor to be here with you to communicate academic questions and ideas. Today, my presentation is about redundant routing provision in a FlexE or WDM network based on segment frame replication and elimination. The outline of my talk is as following. The first part is the background of this research. The second part introduces the key technology of the research. And then the third part details system architecture and introduces the redundant routing heuristic. Then, in the fourth part, the simulation results demonstrate the performance. And at last is the conclusions. Ultra-reliable and low-latency communication is one of the three application scenarios of the fifth generation. In recent years, stricter requirements are put forward for the latency and reliability of the fifth generation barrier network. In order to achieve high reliability, some classical mechanisms have been proposed, such as automatic repeat request and 1+1 protection. In Layer 2, time-sensitive networking provides seamless redundancy character for Ethernet network by frame replication and elimination for reliability. It replicates mic frames of a client flow at a source noodle or relay noodles, and duplicated frames will be routed through redundant paths. Then, either original or duplicated frames will be eliminated at a destination noodle or other relay noodles. Replication and elimination for reliability has much lower latency than automatic repeat request and has lower redundancy than 1+1 protection. Before we deal with the challenge, we need to introduce a key technology, flexible Ethernet over wavelength division multiplexing. It is considered as a promising approach by means of bundling or dividing physical Ethernet interfaces into multiple hard slices over WDM to support deterministic transport. Let's look at the illustration in this slide, the electric layer of FlexE over WDM. Inside the IP router, a FlexE shim layer is added to map mic flows to a desired set of physical interfaces. Each PHY is physically associated with an IP router. A set of logical bounded PHYs forms a FlexE group. The interface between routers and the WDM layer is the transport box, which connects the PHYs through the client-side ports and creates optical channels at a given bit rate through optical transponders. In this research, we considered a FlexE unaware transport architecture, in which each of the Ethernet PHYs is carried independently over the transport network, using a physical coding sublayer. Then we introduced the transport network architecture of FlexE over WDM with frame replication and elimination. At the WDM layer, ROADM is used to routing multiple wavelengths to different destinations. Only flows from the same FlexE shim can be mapped to the same FlexE group, and a FlexE group may be carried by one or some wavelengths, which should be co-routed in the networks. Before client flows come to the FlexE shim, frame replication and elimination is executed at mic layer to improve flow reliability, and the noodles that perform frame replication and elimination functions are called function noodles. Most of iterators related to replication and elimination consider to replicate mic frames at a source noodle and eliminate them at a destination noodle, which is equivalent to an end-to-end protection, but it may cause resource overprovided, especially in a real network scenario. Different links and noodles have different packet loss probability, and client flows show diverse reliability requirements. To this end, we propose segment replication and elimination to ensure the reliability of flow. In order to deal with the challenge, we first propose the reliability evaluation model based on mixed cut set. The illustration in this slide shows a routing graph in which the width represented the packet loss rate of links and noodles. To evaluate reliability, we use the connectivity of the terminals to represent it. The way to calculate the connectivity is to enumerate all possible failure states which cause the terminals to be disconnected. Each failure state includes noodle failures and link failures. and the field nodes and links consist of a mixed cut site. For each failure state, the probability of occurrence is equal to the product of package loss rate of all nodes and links in the mixed cut site. And the failure states could be divided into 3 cases, which are shown in the illustrate. The connectivity is obtained by calculating the probabilities of all failure states. By considering the difference of link and node packet loss rates and Java's flow reliability requirements, redundant routing provision based on segment frame replication and elimination aims to provide segment protection to condense the network redundancy. The algorithm is divided into 2 parts: deploy function nodes in the network and calculate routing graph for all client flows. First, we deploy the function nodes by scoring the nodes according to the entropy weight method, and sort nodes. We deploy function nodes according to the node order from the smallest to the largest, and we initially set all nodes in the network to be the function nodes, and then we will calculate the routing graph for the client flow. First, we choose an available path with the highest reliability as a working path, and then we will calculate the redundant path for the client flow. We select the source node and the destination node for duplicated frame according to the node scores, and then we will choose an available path between 2 nodes as the redundant path, and then we will update the routing graph for the client flow and evaluate whether the current reliability meets the reliability requirement of the client flow. If it is not satisfied, we will keep increasing the number of redundant paths. Finally, we will record the number of unused function nodes in the routing graph and change the number of deployed function nodes for the next iteration. Then we will go back to step 1 and loop. The algorithm will repeat until we find the minimum number of deployed function nodes while meeting the reliability requirements of all client flows. We evaluate performance in 14-node network. Parameters of simulation environment are listed in the table below. We also propose the other 2 comparison algorithms. The first one is to provide end-to-end protection for client flows, and the selection of the redundant path is based on the number of non-consistent links in the routing graph. The second one is to provide segment protection for client flows. The selection of the redundant path is based on the function node selection, which is to select the function nodes along the routing graph in turn. Finally, we introduce the simulation results. We first compare the guarantee of the reliability requirements and the resource utilization under different reliability requirements. We can see that this algorithm maintains a good performance both in reliability and resource consumption, and the growth rate of the consumed bandwidth and router cards for the method is the lowest under ultra-reliable requirements. Then we compare the guarantee of reliability requirement and the resource utilization under different number of deployed function nodes. When the reliability requirements of the client flow is ultra high, and we compare the two methods which can provided segment protection for the client flow because the selection of function noodles is determined before redundant routing for the client flows. And we can say that the method also get a good performance. In this research, we first designed a reliability evaluation model based on mixed cost set, and then we proposed the redundant routing provision based on segment frame replication and elimination to achieve an ultra-reliable and energy-efficient transmission. And we evaluate the performance of the proposed algorithms by simulation results. And last, a lower complexity and more intelligent algorithm needs to be considered, such as reinforcement learning. That's all. Thanks for your attention.
So, thanks to the speaker for the presentation. Any question from the audience? We have time for 1 or 2 quick questions. So I just have a comment. Maybe I require a comment also from the author. Maybe Shin, if you want to turn on your camera too, you are very welcome to do so. You said that in the future you will use you plan to use reinforcement learning. Do you think it's more applicable for such a problem, or which limitation do you envision in that context? Why specifically reinforcement learning can improve your solution?
Can you hear me?
Yes.
Because my method is take a little long time because of the much times of iteration to find the minimum number of the function noodles deployed in the network. So I want to use the intelligent algorithms such as the reinforcement learning because it may reduce the complexity of my method and take a smaller time to get the function noodles. That's my answer.
Do you expect that reinforcement learning can improve also so not only the scalability but also the quality of the solution?
Sorry.
So the optimality. You are saying, if I understand correctly, that reinforcement learning will be a good candidate to reduce to improve the scalability of the problem, no? So to obtain a solution in shorter time. But do you expect that reinforcement learning also has a better solution, not only faster, but also, I mean, better, I don't know, perhaps in terms of number of required nodes, paths, and so on? Or it's only scalability, the main concern that you want to address with reinforcement learning? Can you hear me? Keshin, we cannot hear you. I'm not sure you are talking, but we cannot hear you. So my question, I just repeat the question if you can answer, otherwise we move on. But the point is, do you only think that scalability is an issue and so you use reinforcement learning, or you also want to improve your solution? I think there might be some problem with the audio of Keshin, so
Yeah.
perhaps we move forward and we leave the question for later. So the next so let me thank the speaker, Keshin Wu, and let's move to the next one, to the final one of this session, which is latency aware and survivable mapping of VNFs in 5G network, edge and cloud, from Prabhu Kaliammal Tiruvasagam. And now I'm going to share the video.
Welcome to all. In this presentation, we are going to see latency aware and survival mapping of VNFs in edge computing enabled 5G networks. In the introduction, we will see the evolution of mobile networks and different 5G use cases and the role of NFV in 5G networks. Then we will discuss different 5G network architecture models. Then we'll discuss the problem statement. Then we'll see edge computing selection strategy. Then we'll see modeling and complexity of the problem. Then we'll discuss the proposed heuristic design to overcome time complexity. Then we'll discuss results. Finally, we'll conclude the talk. Since 1980, roughly for every decade, a new mobile communication technology is being introduced. Till 4G, services were designed to support human-centric services, such as voice and multimedia applications. But 5G is designed to support both human-centric and machine-centric services. Here, machine-centric services mean without human intervention, devices, machines, and vehicles can communicate themselves to provide services. So 5G can support multiple industry verticals such as transportation, agriculture, manufacturing, healthcare, etc. 5G use cases are broadly classified into three categories. The first one is enhanced mobile broadband, which supports high data rate applications. The second one is ultra reliable and low latency communication, which support mission critical applications. The third one is massive machine type communications, which support to provide connectivity to billions of Internet of Things devices. In this work, we focus on ultra reliable and low latency communications. Multiple network functions are used to provide services. In traditional network, these network functions are designed as hardware appliances. However, designing hardware appliances is expensive and it takes more time to design, test, deploy, maintain, update, and upgrade. To overcome these issues, a new concept called network functions virtualization was introduced. NFV enables to run these physical network functions as virtualized network functions on top of general purpose hardware such as switches, routers, and servers. NFV provides flexibility and enables to reconfigure network functions dynamically. So NFV is considered as one of the key technology enablers for 5G for provisioning services dynamically. Here we consider an NFV enabled 5G network. In this network, user service requests are passed to core network through access network for provisioning services. But some service requests like self-driving cars have extreme low latency requirements. So processing user service requests at core cloud may violate latency requirements of the users. In this architecture, computing facilities are moved to the network edge to meet the latency requirements of the users. MEC enables to provide delay sensitive services and it consumes less bandwidth and enhances privacy and security. However, this approach is expensive because edge cloud is located at each base station and the available resources may not be utilized efficiently. The other option is edge clouds can be located at selective locations of the network to reduce cost, but we have to make sure that the latency requirements of cell edge users also can be satisfied. In this work, we consider the second type of architecture and try to address the following questions. How to select the potential locations for edge clouds such that the number of edge clouds required to cover the entire network can be minimized, and how to place VNFs in different edge clouds to meet the diverse service requirements of the users and industry verticals, and how to handle the failure of VNFs without interrupting services. Please note that edge cloud is also referred as multi-access edge computing and mobile edge computing. Here the problem is, for the given input of a physical network graph and a set of service requests, we have to find an efficient mapping of VNFs onto the edge cloud such that the overall service provisioning cost can be minimized while ensuring survivability and meeting the requirements of the users. Here we consider MEC selection strategy. In this work, we use closeness centrality metric to find how close a node is with respect to all other nodes in the network. Actually, CC measures the mean distance from a node to other nodes in a contained network. CC value of a node can be identified using this expression. Here, the distance denotes the shortest path distance between nodes. Since centralized nodes are closer to all other nodes in the network, centralized nodes can be reached in short time and it can be used to reduce latency. In this work, we select high CC base station nodes to establish MEC cloud facilities. Here, an example is given to show how to calculate CC value of a node in the network. Here, a 5-node network is given. To calculate CC value, first we have to compute distance matrix. Here, a unit distance between adjacent nodes is considered. A shortest path distance from node A to A is 0, node A to B is 1, node A to C is 1, node A to D is 2, node A to E is 2. Similarly, we can compute distance value for all other nodes in the network. The distance matrix computed, we can compute the total distance from node to all other nodes in the network. It is nothing but the sum of row values in the distance matrix. Once we have the total distance, then we can compute the CC value of a node. From this calculation, we can see that the node C has high CC value. That means C is the centralized node in the network. So from this example also, we can see that C is the centralized node in the network. Here we consider latency aware and survivable mapping of VNFs problem. The objective of the problem is to minimize the overall cost, which consists of deployment and maintenance cost of edge servers for hosting VNFs, and license cost of VNF instances for provisioning services, and the traffic forwarding cost, which consists of link bandwidth use and delay between base station and MEC cloud facility. Traffic forwarding cost denotes the cost to forward a packet from one node to another node. Then we model our requirements as constraints. The first constraint is placement constraint. For each service request, the corresponding VNF should be placed in one of the available servers. The second constraint is survivability constraint. For each primary VNF, a dedicated backup VNF should be placed in a different edge server. So if a VNF is failed or an edge server is failed, then it can be handled. Then latency constraint. The total service delay should be less than or equal to the latency requirements of the users. And bandwidth constraint. The bandwidth allocation should be sufficient to satisfy the data requirements of the users. We model the problem as an integer linear programming problem to optimally minimize the overall cost. Actually, the problem is NP hard and we proved it in our paper. Since the problem is NP hard, we use simulated annealing based heuristic design to overcome time complexity. Here, an initial temperature is set, then a feasible solution is generated. A feasible solution indicates that mapping of VNFs onto the edge cloud meets users' requirements. Here, give high priority to low latency requirements, and we follow first fit principle to reuse activated resources. Then a set of new solutions are explored in inner loop for certain number of iterations. Once a new solution is generated, the new solution is compared with the current solution. If the new solution cost is lesser than the current solution cost, then the new solution is accepted directly for the next iteration. Otherwise, a new solution is accepted with certain probability. Here, a random value R is generated between 0 to 1, and the random value is compared with the probability value. Here, the probability value is a function of temperature T and the cost difference between current solution and new solution. If the random value is less than the probability value, then the new solution is accepted. Otherwise, the current solution is retained. This process continued for certain number of iterations. Then the temperature is updated. Here, the temperature is reduced in a controlled manner. Here, A denotes cooling rate. The whole process continues till the actual temperature is less than the threshold value. Here, the proposed heuristic follows unlinked process of cooling the temperature in a controlled manner and allowing bad movement with a certain probability to come out of a local minimum. Here we consider 4 different service types. Each service type has different delay and data rate requirements. In this graph, we compare the delay with respect to number of cloud facilities established. We consider 2 different approaches. One is CC based approach, another is random based approach. CC based approach means the MEC cloud facilities are established based on CC value of a node. Random means MEC cloud facilities are established at random locations. We consider 2 delay. One is average delay, another is max delay. Average delay means what is the average delay to reach one of the MEC cloud facilities in the network. Max delay means what is the maximum delay to reach one of the established MEC cloud facilities in a network. As we see here, if you increase the number of MEC cloud facilities, the delay is reduced. To have the maximum allowed delay of 2 milliseconds, we should have 5 MEC cloud facilities. When we have 5 MEC cloud facilities, the max delay is less than 2 milliseconds. In this graph, we analyze the average total cost for provisioning services with respect to number of service requests. Here we compare our proposed solution with optimal solution. As we see here, our proposed solution performs close to the optimal solution, and the optimality gap is within 3.5%. Here we summarize our work. NFV and MEC are considered as key technology enablers for 5G. We first selected a few potential base station nodes using CC value to establish MEC cloud facilities. Then we model the problem of latency aware and survival mapping of VNFs in MEC as ILP and proved that the problem was NP hard. Then we proposed a simulated annealing based heuristic algorithm to overcome time complexity. Then our simulation results showed that the proposed algorithm provided near optimal solution with the optimality gap of 3.5%. Some of the future directions are, in this work, we designed an offline algorithm to process packets in a batch. Instead, we can design machine learning based online algorithm to predict the future and allocate the resources efficiently. And failure detection and rerouting mechanisms can be designed to analyze the actual delay incurred in the recovery process. Instead of single connectivity, we can go with dual connectivity based user association to improve the reliability of the system. Thank you.
So let's thank the presenter. And if there is any question from the audience for the speaker, for Prabhu, please raise your hand as usual. Guido, do you have a question?
Yeah, I have one question. Maybe he told this, but I missed it. I was wondering what is your cost model when you are calculating the cost, if you can maybe detail some more.
Okay. I hope voice is audible.
Could you switch on your camera so we see?
Yeah, sure. Yeah, that's a good question. There are different costs involved while deploying virtual network function in data center. So there is a procurement cost, a design cost, cooling cost. So we give higher cost to cloud establishment and maintenance. It includes energy consumption cost and operational cost. Then we consider VNF license cost. If we purchase a VNF from a third vendor, we have to incur some cost to get that VNF function. Then we consider the transportation cost. If we forward the packet from one node to another node, then we have to reserve some bandwidth. So we consider cost based on these criteria.
Okay. Thank you. It's clear.
Thank you. Any other question? Okay, so I think we can close the session, but first let's
Maybe
thank all
there
the
was,
speakers.
I don't know if the previous speaker is still on.
Keshin, who is, are you still here? So, Keshin, I don't see, no, I don't see in the participant list here now.
Okay, let's go.
Okay, so I think we can stop now the session. Let's thank all the speakers of these sessions and again the keynote of this morning, Dr. Fujiwara, and now it's time for coffee break. So
yes, before going to
please.
the coffee break, I would like to remind you that this afternoon there will be the Gather.town virtual poster session. I have just sent to all participants the instructions to log in and also the access link. I just want to let you know that since there was the posters from DRCN speakers that were sent to us in order to participate to this session were limited in number. We thought to let's say add to these posters also some presentations from our bonsai lab. So it will be a poster session, but also a virtual visit to the lab, let's say. So you're welcome to join us at 4 o'clock. And since we are 10 minutes late, the next session, that is the industrial panel, will start at about 10:55. Okay, so let's get back here at 10:55. Have a nice coffee.